Hey there, chemists. In this lesson, we're going to look at how we use what's called molecular orbital theory to explain some of the properties that we see in molecules. This is going to tie in with our solid state chemistry unit when we look back at some macroscopic pictures of solids. But I want to actually look at small molecules today to introduce the concept of molecular orbital theory. There's quite a rundown here on your notes that describe what molecular orbitals are. They are combinations of atomic orbitals, what we talked about much earlier in the course, and they create molecular orbitals, which are called MOs. It says that however many you have in atomic orbitals come together to make a molecular orbital. So for example, let's just look at the molecule hydrogen, which is H2. It's the simplest molecular orbital you could ever draw. Hydrogen has one atomic orbital that's occupied. It's the 1s atomic orbital with one electron in it. That would be one hydrogen atom. And then if it sees another hydrogen atom also with a 1s orbital occupied with one electron, those are the atomic orbitals. Atomic. H. What happens when we make a molecule is those atomic orbitals actually combine to make what are called molecular orbitals. One of them, it says, is higher in energy and the other one is lower. And in this case, we draw them also just as lines, just to abbreviate that they can be filled with electrons. There's one that's higher in energy, there's one that's lower. The higher one is called the anti-bonding orbital, and the lower one is called the bonding orbital, and you simply combine all the electrons that the atoms bring to the table to build a molecule. Just like when we were drawing Lewis structures, this is just a very different way of drawing the electron arrangement. So, and we fill them from lowest to highest energy, and I only look at those molecular orbitals. So this is a picture of molecular H2, and those two electrons get to pair up in that bonding orbital, which happens to be what makes up the sigma bond. Remember, we talked about sigma bonds back in the organic unit and even back in the bonding unit originally. We give the notation sigma with an asterisk or sigma star for the anti-bonding orbital. And that's it. That's a molecular orbital diagram for hydrogen, the simplest one. There's also one other thing that says the bond order is based on the combination of sigma bonds and pi bonds. Although for today, we're going to look at this formula where it's the number of bonding minus the number of anti-bonding electrons divided by 2. So hydrogen has a bond order, actually write it, bond order equal to 1/2 of, well, there's 2 bonding electrons, there's no non-bonding electrons, and half of that gives me 1. Which is exactly what I would expect for one single bond between 2 hydrogen atoms. And as long as the bond order is a positive number, you have a stable molecule based on molecular orbital theory. So let's look at some other hypothetical examples. Here's potentially diatomic helium, and then we'll look at the nitrogen molecule, a much bigger one. So diatomic helium has a very similar starting point to hydrogen. It has a 1s orbital and another 1s orbital, but each of them have 2 electrons. Remember, helium's electron configuration is 1s2. That's an atom of helium. They combine to give you a anti-bonding sigma star and a bonding sigma orbital, and I fill those with all 4 electrons. 4 electrons in lets me have 4 electrons out, so I would actually have to occupy the sigma and the sigma star, so I would get a bond order, a BO, is equal to 1/2 of 2 minus 2, that's 0, and that tells me that this is unstable. You need a bond order to be a positive number in order for it to be a stable molecule. So what about the nitrogen molecule? Now nitrogen's a much bigger atom than the other 2. Remember what nitrogen is first of all. Nitrogen's electron configuration is 1s2, 2s2, and then 2p3. And we're only going to look at the valence electrons because that's what's involved in bonding. We're not going to look at the core electrons. So if I look at a nitrogen atom, it has a 1s orbital with 2 electrons in it, and then it has a 2p orbital. Actually, there's 3 p orbitals in the second principal quantum level. 1, 2, 3. That's the 2p orbital. And there are 3 electrons, 1, 2, 3, each occupying singly. That's one nitrogen atom. Let's draw another one just over here to the side. Exactly the same. 1s2, and then 2s2. 2p3. Right, because we are only looking at valence, so it says 2s for each one. Let me just clean that up. 2s, 2s. Now, how do we make molecular orbitals out of this many? The number of atomic orbitals will combine to give you the same total number of molecular orbitals. And I'm going to work my way up and see that I have a sigma and a sigma star for the combination of the 2s orbitals. Now, the p orbitals can combine in a variety of ways. You can get sigma bonds, but you can also get pi bonds. Remember, pi bonds come from p orbitals overlapping, and we list them as well. It turns out that the lowest energy is actually the bonding pi orbitals. Then we get to the sigma bond, and then we get to the anti-bonding pi star, and then the anti-bonding sigma star. There is a complete template for the nitrogen molecule, really a template for most atoms that have 2s and 2p valence electrons. Now, how many valence electrons do we have to build this molecule? We've got 5 valence from each, so I've got 10. So I'm going to fill up those 10 electrons. 2, 4, 5, 6, 7, 8, and then 9 and 10. And notice we actually didn't put anything in those anti-bonding orbitals up above. If you're curious about the arrangement of the sigma and pi orbitals for here, that's so okay. It actually changes as you go across the row. We'll see it in a second for oxygen. All that you really need to know is that the 3 p orbitals from each nitrogen give us a total of 6 molecular orbitals in level 2, and that 3 of them are bonding, 3 of them are anti-bonding, and the pi and pi star are degenerate within each of those rows. That's all you really need to know. So I fill the bonding before the anti-bonding. What's the bond order for a nitrogen molecule? Well, based on this, it would be 1/2 of the bonding, 2, 4, 6, and 8, minus the anti-bonding, which is just those 2. So I get 1/2 of 8 minus 2, that's 1/2 of 6, that's 3. And when I hear that, I think, yeah, a nitrogen molecule has a triple bond in it. So it makes sense. For these little binary molecules, the bond order will match the type of bond that you see between the 2 atoms. When you get to bigger molecules, that's not true, because bigger molecules have large molecular orbitals, and you'll actually start to get fractions for the bond order. But it still makes sense when you take the weighted average of the types of bonds you see. Okay, so I said that this explains some properties of substances, and one thing that this helps us explain that sometimes valence theories, Lewis structures do not, is the attraction or repulsion to magnetic fields. We talked about this a long time ago for atoms, but it's more relevant when we talk about molecules. The definition is the same, however. If a substance has an unpaired electron, it is attracted to a magnetic field, and as a result, it is called paramagnetic. However, if it only has paired electrons in the molecular orbitals, it is not attracted to a magnetic field, it's actually repelled, and it's called diamagnetic. So, for example, nitrogen has all paired electrons in the molecular orbitals, so it would be a diamagnetic molecule. If I took liquid nitrogen and poured it over a very strong stationary magnet, I would not see any attraction to that magnet. I might even see some repulsion. However, many species have unpaired electrons in their molecular orbitals, and even though they look like they are nonpolar molecules with no possible way that they could be attracted to a magnetic field, it's their electronic arrangement that we use to explain this observation. For example, this is true for oxygen. In fact, I have 3 examples for oxygen. In the molecular orbitals here, the templates are already given. Notice the level 2 sigma and pi system is actually flipped from nitrogen. Again, it's sort of beyond the scope of our class right now about why that is. All that's important to know is that you have 3 bonding and 3 anti-bonding from the combination of the 2p orbitals. How many valence electrons do we have? Well, let's just refresh our memory on what oxygen looks like. Oxygen as an atom is 1s2, 2s2, and 2p4. Each one is just one more than nitrogen. So if I think about the valence only, that means there's 6 valence electrons for each oxygen. So O2 would be 12 valence electrons. And since the template's already there, that's much more convenient, I can just fill them from low to high. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11 and 12. And lo and behold, I have unpaired electrons. This is a paramagnetic molecule. Liquid oxygen will be attracted to a magnetic field. Liquid O2 is attracted to a magnetic field. I'm probably writing that right on top of my screen, so I will move it up. That's what it says. Liquid oxygen is attracted to a magnetic field. Wait, isn't gaseous oxygen also attracted? Well, it's easier to see with liquid, so there's great videos of this online if you want to search for it. What about the other 2 examples? This is the oxygen, molecular oxygen cation. That's just 1 electron less. And oxygen negative would be 1 electron more. So these are odd-numbered species. So O2 plus would be 1 electron less than what we just drew. And then O2 negative would be 1 electron more than what we just drew. And if you have an odd number of electrons, it's got to be paramagnetic. So all of these are actually paramagnetic species, the cation, the anion, and the original molecule. Okay, so that's an introduction to molecular orbital theory, just for some simple, small, and all binary molecules. This can be applied to larger molecules. We're going to apply it to solid species and use that to explain some of the very interesting properties of solids when we get to the next lesson.